Given two surfaces and a sparse set of corresponding landmarks, our method generate compatible meshes which possess the same connectivity structure. High-quality compatible meshes usually satisfy the following properties. Two output meshes have identical connectivity structure. Two output meshes are fairly regular. The approximation error between each input mesh and the corresponding output mesh is bounded. The complexity of the output meshes is as low as possible. The piecewise linear mapping is with low distortion. It is challenging to adequately satisfy these requirements all at once, since these requirements are coupled with each other. One possible way to overcome this difficulty is to decouple these requirements. First, relax some of the constraints and solve the new problem for an intermediate solution. Then use it as an initialization to seek for a solution that meet all the constraints. We develop a two-stage approach, which first generate compatible meshes with bounded approximation errors and fairly regular, and then reduce mesh complexity while maintaining compatibility, regularity, and bounded approximation errors. In the first phase, we develop a parametrization-based method to generate compatible meshes. It requires two corresponding cuts and a pair of target edge length fields. To satisfy the error-bounded constraint, we alternatively adjust the target edge length fields to guide the boundary to interior compatible remeshing. If the error-bounded constraints are satisfied, we stop the algorithm. Here we go detail into the boundary to interior compatible remeshing. First, the corresponding cuts are consistently remeshed using arc length parametrizations. With the remeshed cuts, we compute bijective parametrizations of the disk topology meshes under the common boundary conditions. Then we perform edge-based compatible remeshing based on a fusing target edge length field while fixing the boundary. Finally, we use the bijection lifting method to generate compatible meshes. We develop an alternating algorithm to reduce mesh complexity. In each iteration, we iteratively use a compatible target edge length field to perform consistent remeshing, while ensuring bounded approximation errors and increase the compatible target edge length field. If the termination conditions are satisfied, we stop the algorithm. Our edge-based compatible remeshing process uses a series of locally compatible operators. We use a short video to show how the mesh connectivity structure changed in one iteration. 4 state-of-the-art methods are selected as competitors. Since these competitors keep the topological structure of one mesh unchanged, the resulting mesh quality depends on the quality of the input mesh. We find that all the compatible meshes generated by competitors violates the error-bounded constraint. The violation usually arise in regions with rich geometric features. In contrast, the results of our method have much less vertices than that of the competitors. And we are able to satisfy the error-bounded constraint in each of the examples tested. The mappings between the resulting compatible mesh pairs of our method have lower distortion than that of the competitors. Here are more results. We test our method on a dataset consisting of 102 models. And our method successfully generates compatible meshes that satisfy all the requirements. Here we show 10 pairs of models. On the left are the connectivity structure, and on the right are the texture mapping. The number of vertices, the Hausdorff distances, the average of the smallest angle of each triangle, and the average distortion over all the triangles are reported below. Thank you.